This behavior that we saw in the previous video, the behavior of the magnetization with respect to the temperature T, is a kind of behavior that is typical of phase transitions, when we have a variable that changes in a somewhat discontinuous way, or if not discontinuous, at least in a sharp way, just like you can see here. When we decrease the temperature at some point, we have a sharp change in the magnetization. But we can also have a different type of phase transition when we have a discontinuity, and this case is related to the heat capacity, for example. So the heat capacity C is defined as the change in the average energy with respect to the temperature, and the average energy can be calculated by means of the partition function. In particular, this is equal to minus the derivative with respect to beta, the parameter beta, of the logarithm of the partition function. We can also substitute this expression there, but a more convenient way to write the expression, since here we have a derivative with respect to the temperature and here we have a derivative with respect to beta. Remember that the temperature and beta are related because the temperature is equal to 1 over beta, assuming that the Boltzmann constant is equal to 1. We are using units such that the Boltzmann constant is 1 for convenience, just for simplicity. The derivative with respect to the temperature, according to the chain rule, can also be written as d beta dt d over d beta. If we take the derivative of beta with respect to the temperature, since beta is equal to 1 over t, from here, beta is equal to 1 over t, therefore this can also be written as minus 1 over t squared derivative with respect to beta, or if you want, minus beta squared derivative with respect to beta. Therefore, the heat capacity can also be written as beta squared second derivative with respect to beta natural log z. Now, it is quite simple to write the expression for the partition function if the temperature is greater than the critical temperature, because in this case we know that the minimum value for the magnetization is equal to 0. And therefore, remember that we have to calculate F at the point M min. But the minimum value for F, if we disregard the constant term, just like in the previous lectures, if you recall, we had a constant term in F of the kind temperature times the natural log of 2. But such terms can be simply disregarded because they are not important in general, so they are just constant terms that do not affect the physics that we are considering, because when we write the logarithm of the partition function and we take derivatives, these terms do not cause any kind of contribution. So basically what we can say is that this is 0. But remember that the partition function z is approximately e to the minus beta capital N f of m min, and when we take the logarithm of z, this is equal to minus beta n f of m min. But of course, if this is 0, the natural log of z is 0, and therefore also this derivative would be 0. So from here we see that this heat capacity is 0 if T is greater than Tc. But what happens if T is smaller than Tc? Well, in this case we don't get a trivial result. We don't get 0. And how can we see that? Well, we can see that because if you recall, when T is smaller than Tc, m min is equal to plus or minus some value that last time we called m0. So if you recall, the expression was plus or minus square root of 3 Tc minus T divided by T. If you consider this term and you plug it in the expression for f min, for f of m actually, so you have the expression for f of m that we also used in the previous video, in particular this expression here that we expanded in powers of m by expanding the natural logarithms there. Remember that the magnetic field is 0, so when you put those values here, and you can see that we have even powers of m, so you can plug in plus this value, where is it? Plus this value or minus this value, you get the same result. We are going to consider only the terms up to the fourth order. So if you consider the expression for m, the minimum value for m here, and you plug it into f of m, so you calculate f of m min, what you get is the following result. So this is approximately, in general I should write an approximation symbol, minus 3 over 4 tc minus t squared divided by t. Then we have to use this result in here to calculate the natural log of z, and we also have to calculate this heat capacity here. So when you consider derivatives, d squared d beta squared, this can also be written as minus 3 over 4, and then if you want you can write this in the following way. So you can factor out t squared from here, so you can write tc over t minus 1 squared divided by t. So this is equal to minus 3 over 4 t times, and then here you have tc times beta minus 1 squared, and this t can also be written as 1 over beta. So you have minus 3 over 4 tc beta minus 1 squared over beta. So you can see from here that we get beta times f of m min equal to minus 3 over 4 tc beta minus 1 squared, like this, which appears, this expression appears in here. So the natural log of z is equal to minus, we have capital N, 3 over 4, and then you also have this minus here, so pay attention to that. So this will become a plus tc beta minus 1 squared. So when you consider the second derivative with respect to beta of this, of natural log z, this will give rise to n3 over 2 tc squared. This is what you get. Therefore, from here, when you multiply this by beta squared here and beta squared here, what do you get? Well, what you get is simply, where is it? This expression here. So you have the heat capacity, which is just n times 3 halves times tc over t squared. As tc gets closer and closer to t, of course, this will become approximately 1. Therefore, the heat capacity divided by n, so this is the specific capacity, equals 0 as t becomes closer to tc from the right. So t is slightly greater than tc, and it is equal to 3 halves as t approaches tc from the left. So it is slightly smaller than tc. So we can see this jump, this discontinuity in the specific heat capacity or just in the heat capacity.